All right, here we go. AP Physics video on circular motion. All right, most of this is going to be a review from what we did last year. A little bit of new stuff here, so I will try to make sure that as I'm going through this, I comment on what's new. All right, so here we go. So everything here is stuff you know. Uniform circular motion. All right, a particle is in what we call uniform circular motion if it is A, traveling in a circle, or even just part of a circle, you know, like going around a circular curve or something. It's only called uniform circular motion, though, if the speed is constant, okay? And most of what we're going to do this chapter is constant speed. Towards the end of the chapter and as we move forward, we'll start to look at what happens if something is changing speed as it goes in a circle, all right? Now, remember, velocity is speed and direction, okay? And since as your object is going in a circle, the direction is always changing, right? That means that it is accelerating, even though it's not speeding up or slowing down. All right? Now, it turns out that as long as you're in uniform circular motion, your object will have a velocity and an acceleration which have constant magnitude. In other words, numerically, the velocity and the acceleration are constant, but their direction will be constantly changing, okay? And I'll talk in a minute about how to, you know, sort of what the relationships are between those directions, okay? So, now, when you've got an object that is traveling in a circular path, the acceleration that it experiences due to the changing velocity, specifically, I almost wish that it said the changing direction. So the acceleration experienced due to the changing direction of an object following a circular path is called centripetal acceleration. All right. The word centripetal, the Greek roots of it actually means center seeking, if you care, which means that it's always pointing towards the center. Again, I'll talk about that in a second. For now, what we need to remember is that to calculate centripetal acceleration, you take the magnitude of the velocity squared and divide it by the radius. Notice I did not label any of these as vectors. That's because this equation simply gives us the magnitude of the acceleration, okay? Now, if you want to know where this equation comes from, it requires a little bit of calculus and a little bit of geometry. I don't usually go through it because most students don't care. If you're particularly interested, let me know in class and I'm happy to run through it with you, okay? All right. All right, so two other quick definitions. You need to make sure you understand what period and frequency are. So if you don't remember, the symbol for period is the capital letter T, and that is defined as the number of seconds that it takes for an object to complete one revolution. All right, and frequency is the number of revolutions that your object completes per unit time. Okay? And so it turns out that if your speed, as long as your speed is constant, you can calculate the magnitude of your velocity by taking the circumference of your circle, right? That's how far it travels per rotation, and dividing it by the time it takes, which is equivalent to multiplying the circumference of the circle by the frequency, okay? So, and again, notice not vectors here, right? This is just to calculate the magnitude of the velocity, all right? So, let's talk now about direction, all right? So, as you've got an object that's traveling in a circle, there are a number of vectors that we can look at, all right? So here's my object going in a circle. Pretty happy with that circle that I drew? All right, here's the center of the circle. All right, so if I look at the object, so suppose my object is spinning in a circle and at some instant it's right here, okay? So one of the things that I could measure at that point is the position, all right? Now, assuming that the center of my circle is my origin, which it doesn't necessarily have to be, then my position vector is this, right? Okay. So I guess I should comment too that this R here is meant to be radius, not position. Okay. Just in case your origin isn't at the center. Okay. Same with Same with this radius. This is the radius of the circle that it's traveling in, okay? All right, so there's my radius vector, okay? All right, now there's also a velocity vector, right? So I have, I can put this arrow here indicating that it looks like this thing is spinning, what is that, counterclockwise? All right, so it turns out that in the same thing that we learned in, what was it, section 3.2, an object's velocity vector is always tangent to the path that it follows. In this case, it's tangent to a circle, which means that my velocity vector is actually perpendicular to the radius. Okay, so let's make a note of that. In fact, I'm going to do this. There. I'm just going to get rid of this because it's in my way. All right, so here's the first thing we've learned. Our velocity vector will always be perpendicular to the radius vector. Okay? Now, acceleration. Well, remember, your acceleration is always directed inwards towards the center. Okay? As is your centripetal force, right? Which, although we're not doing force yet, that's hopefully a thing you remember from last year, right? Okay? So if you look at this, notice the red radius line and the green acceleration line point in opposite directions. So we say that those are anti-parallel, all right? So I'm going to write this. It turns out that your acceleration vector is anti-parallel. So this would be the symbol for parallel, right? So anti-parallel, I don't even know if this is real notation or if I made this up, but I make it two little arrows, one points up, one points down, to indicate that they're parallel but opposite directions. So our acceleration vector is anti-parallel to the radius vector. That means that our velocity is also perpendicular to the acceleration. Okay? And then remember, your centripetal force and your acceleration always point in the same direction. So our centripetal acceleration is parallel in the same direction with our centripetal force. Okay? So that is that. All right, so let's apply all this to a problem. So it says an object moves at a constant speed along a circular path in a horizontal xy plane with the center at the origin. When the object is at x equals -2, the velocity is -4j. So let's draw it. Here's our circle. Here's the center. Center's at the origin. X and y axes. It says when the object is at x equals -2, the velocity is -4j. So let's draw on our vectors. Here's our radius vector, our velocity vector, which I believe last time I drew in blue, so let's stick with that color coding. Here's our velocity vector. It's -4. I guess I don't need the negative, the arrow. Well, whatever. 4 meters a second. I guess we can put negative and put a j on it, right? So it wants the velocity and the acceleration at y equals 2. So the idea is sooner or later there's going to be a point where the object gets to over here. So now we've got this new radius vector. It's still a magnitude of 2, right? But it just points in a different direction. And if this velocity is down, then it must be going around this way, which means by the time it gets to here, it's going this way. So for part A, the velocity there, well, it's uniform circular motion, so it's still going at 4 meters a second, but now it's in the negative I direction, right? Because it's pointing to the left, and there's no vertical motion at that point. Cool. And then to find our acceleration, oh no, it's not at all what I wanted to do. Do this. To find our acceleration, remember it's v squared over r, so our velocity is 4 meters a second. Notice, remember, this is just the magnitude of the velocity divided by our radius, which is 2. So 16 divided by 2 gives you 8 meters per second squared. The units do work. And remember, when it's at this point up here, remember your centripetal acceleration always points towards the center. So it should be -j. Okay? So Next example. So we got a small particle spinning clockwise in a circle at a constant speed in the xy plane. The circle is centered at the coordinates 4, 7. Yeah. I remember this problem. All right, I'm going to pause this for a second while I draw my coordinate system. Okay, so I made an xy axis here, and I just sort of marked off, by ones. So our center is at the point 4, 7. So 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. So here's my center. All right, it says at time t1 equals 4 seconds, the object is at a point of 4, -3. So that's at t equals 4 seconds. And so worth noting that this radius vector here, let's call this our initial, is 10 meters, right? Right, just from +7 to -3. Okay, let's see. And at t equals 7 seconds, it's at -6, 7. 1, 2, 3, 4, 5, 6, 7. So that's at, what did I just say? T equals 7. All right. Same radius, right? Okay. Assuming the particle hasn't completed a rotation. It also tells us that it's spinning clockwise, right? So clockwise is going to be this way. Draw it, I believe. So, okay. So let's do this. All right. So it looks like from t equals 4 to t equals 7 seconds, we went through 90 degrees, right? So that means that, so this is what, 3 seconds? So if it takes 3 seconds to go through 90 degrees, it would take, what, 12 seconds to go 360 degrees, right? So that means my period is 12 seconds, right? Okay, so part A says, assuming the particle hasn't completed a rotation, so that's where I got the 90 degrees from, find the particle speed. Well, speed is the magnitude of velocity, so that's just 2 pi r over t. So 2 times pi times 10 meters in 12 seconds. It gives you a number that I have written on a piece of paper that I wasn't smart enough to grab. Sorry, it gives you 5.24 meters a second. Okay. All right, so that's part A. So let's make a note of that. The magnitude of our velocity is 5.24 meters per second. All right. All right, now part B says find the particle's velocity in unit vector notation at t equals 8 seconds. Holy schmoly. All right, so let me get rid of this guy. So the idea is at 4 seconds, my object is here. After 7 seconds, it's here. So after 8 seconds, it's going to be over here somewhere. But we need to figure out where, right? Well, if in 3 seconds it went through 90 degrees, that means it's going through 30 degrees per second, right? So if it's here after 7 seconds, it's going to be here after 8 seconds. So that this angle in here is 30 degrees, right? So let's see what we can figure out here. So at t equals 8, here's what we know. So this is 30 degrees. We know that our radius is 10 meters. We know that our velocity vector, remember the velocity vector is perpendicular. I don't want to write that there. So remember, our velocity vector is perpendicular to our radius vector. Okay, so I also know that the magnitude of my velocity is 5.24 meters a second. So I'm going to do a little bit of trig here. So let's see, there's an x component to my velocity, and a y component to my velocity. So let's see, if this is 30 degrees, then alternate interior angles tells me that this must also be 30 degrees, which means that this is 60 degrees. So now I can do a little bit of trig and find my Vx and my Vy. Doing that makes my Vx 2.62 meters per second, and my Vy is 4.54 meters a second, just by using a little bit of trig, right? Because I know this angle here is 60 degrees. So for part B, it looks like my velocity is 2.62I plus 4.54J meters per second. Okay. All right, and then for part C, it wants the acceleration at that same time. So, well, first we got to calculate the acceleration. So the magnitude of our acceleration is v squared over r. Well, we know our velocity. We know our radius. So the acceleration, if you calculate it, is about 2.75 meters per second squared. Okay? And the direction of it is opposite the radius, right? So remember, we had decided that at t equals 8, this was 30 degrees, right? T equals 8 seconds. And so our acceleration vector should point in the opposite direction, right? So here's my 2.75. This is 30 degrees. Here's my acceleration horizontally. Here's my acceleration vertically. So again, do your trig and figure out your components, all right? So your AX ends up being 2.38 meters per second squared, and the Y component is negative 1.38 meters per second, squared. So the acceleration centripetally, that's a weird word, is 2.38I minus 1.38J meters per second squared. I'm nervous that those are both 0.38. I'm worried I made a mistake. I'm going to check that real quick. And nope, I was right. Okay, so there we go. All right, so a lot of it is, just kind of splitting your vector up into components. All right. Okay, so last but not least, what happens if the motion is not uniform? In other words, what if the speed is changing? Okay, this is definitely not the emphasis, but I want you to see this at least once before we finish this chapter. So in this one, we've got a toy car on a circular track with a radius of 0.75 meters. It begins at rest and speeds up at a rate of 3 meters per second squared. All right, so now there are two types of acceleration. So I'm going to go over here and do a little scratch work. So here's my circle that the thing is traveling around. Let's suppose it's going this way. Oh shoot, my changes that I made are wrong. Darn it. Okay, anyway, so suppose it's going around this way, all right? So when the car is here, for example, because it's going in a circle, there is centripetal acceleration pointed towards the middle, all right? And to be honest, eventually we're going to call this radial acceleration because it acts along the radius, okay? So there's our centripetal acceleration, right? And then there's also what's called tangential acceleration, which is a measure of how quickly the speed is changing. So if it's speeding up, your tangential acceleration will go this way. If it's slowing down, it would go this way, okay? All right, for us, our object is speeding up, okay? So your overall acceleration then is the vector sum of those. So you have to take this guy and put it over here to find out that your acceleration overall points that way, okay? Notice it's a right triangle, right? Because your radius and your velocity are always perpendicular, okay? So, let's see. So we want to figure out what the acceleration is after half of a lap. Well, we know our tangential acceleration. The rate at which our car is gaining speed is 0.30 meters per second squared. So now what I need to do is find my centripetal, also known as radial acceleration. So I can solve this. Oh, well, that's v squared over r. So what I need to do is I need to figure out what the velocity is after half of a lap. Okay, well, after half of a lap, our displacement that we would have gone through along the path of the circle is half of the circumference. That's pi r, right? We know our initial velocity is 0. We know our acceleration is 0.3 meters per second squared. I guess I can multiply. What's a radius? 0.75. So whatever 3/4 of. So pi times 0.75. So our displacement is 2.36 meters. So now I can use 2a delta x equals vf squared minus vi squared to find the velocity once it's gone halfway around the track. And if you do that, your final velocity ends up being, I don't trust my work, so I'm going to recalculate it real fast. So it's 2 times that times that, and then square root 1.19 meters per second. So now I can find my centripetal acceleration by plugging these numbers in. So squared divided by 0.75, and it gives you 1.88 meters per second squared, right? Okay, and so then the idea is, and I made this change, but the power went out earlier today, so it apparently didn't save. I wanted you to assume that that you started here on your circle, so after half of a lap, you're going to be here, right? Okay, so what we know then is at that instant, our tangential acceleration is the 0.3 meters per second squared, and the radial or centripetal acceleration is 1.88 meters per second squared. And so my overall acceleration is the vector sum of these. Oops, that's not what I wanted to do. Means I have to move that over there, right? And so then my actual acceleration is this guy, right? So you could either write it out in unit vector notation, so we'd say the acceleration is what? Negative 0.3 I minus 1.88 J meters per second squared, or you can put it in magnitude and direction form, right? Okay, so there you go. I think I'm done, right? All done.